Welcome everyone. Today I'll walk you through ultrasonic testing or UT, one of the most powerful NDT methods used in industrial inspection. Principles, applications, and inspection guidelines based on API 577 and ASME Section 5. We'll cover how it works, where and when it's applied, and the rules that guide its use. Please be informed, this summary is intended to simplify the content based on the presenter's interpretation. Ultrasonic examination or UT general overview. Ultrasonic testing or UT is a non-destructive testing or NDT method. It uses high-frequency sound waves to inspect materials and components for internal flaws like cracks or voids. The method also measures thickness and characterizes material properties. A transducer sends sound waves into the material, which reflect off internal structures or defects. The transducer detects these reflections. Analysis of the reflections reveals information about the material's condition, such as corrosion, fatigue, or manufacturing defects. This allows engineers to detect issues before they lead to failure. In simple, UT uses high-frequency sound waves greater than 20,000 Hz to detect flaws inside or on the surface of metal. The sound travels through the metal and reflects back when it hits a flaw, creating an image that shows the size and location of the flaw. How ultrasonic examination or UT works. Number 1 is sound wave transmission. A probe, containing a piezoelectric crystal, converts electrical energy into high-frequency sound waves. Number 2 is coolant. A liquid coolant, like oil, grease, or water, is applied to eliminate air gaps between the probe and the material, allowing for efficient sound energy transfer. Number 3 is reflection and detection. The sound waves travel through the material, reflecting off any internal boundaries, such as flaws, cracks, voids, or the back surface of the material. Number 4 is signal analysis. The probe also acts as a receiver, converting these reflected sound waves, echoes, back into electrical signals. Number 5 is display. The electronic equipment, often with a screen, analyzes the time and amplitude of these reflections to provide information about the material's internal structure. Ultrasonic examination or UT technique, straight beam or 0 degree, used to measure thickness or detect internal layers. The sound goes straight through the material and reflects back. Angle beam or shear wave, used to inspect welds. The sound enters at an angle and reflects off flaws, helping identify their type and position. Types of displays of ultrasonic examination or UT. Number 1 is A-scan, shows signal strength versus time. Helps measure depth and size of flaws. The A-scan, as shown in this figure, is the most common display type. It shows the response along the path of the sound beam for a given position of the probe. It shows the amplitude of the signal coming from the discontinuity as a function of time. The x-axis, right, represents the time of flight and indicates the depth of a discontinuity or backwall, thickness. The y-axis shows the amplitude of reflected signals, echoes, and can be used to estimate the size of a discontinuity compared to a known reference reflector. Types of displays of ultrasonic examination or UT. Number 2 is B-scan, shows a side view, cross-section, of the object. Indicates flaw position along the surface. The B-scan display, see this figure, shows a cross-sectional view of the object under test by scanning the probe along one axis. The horizontal axis, left, relates to the position of the probe as it moves along the surface of the object and provides information as to the lateral location of the discontinuity. Echo amplitude is usually indicated by the color or gray scale intensity of echo indications. Types of displays of ultrasonic examination or UT. Number 3 is C-scan. It shows a top-down view, plan view. Indicates flaw location in XY coordinates. The C-scan display, see this figure, shows a plan view of the test object. The image is produced by mechanically or electronically scanning in an XY plane. The X and Y axis form a coordinate system that indicates probe/discontinuity position. Color or gray scale intensity can be used to represent depth of discontinuity or echo amplitude. Types of displays of ultrasonic examination or UT. Number 4 is D-scan. It is similar to B-scan but shows depth from a different angle. Useful for weld inspection. The D-scan display. See, this figure shows a through-thickness view showing a cross-section of the test object perpendicular to the scanning surface and perpendicular to the projection of the beam axis on the scanning surface. The D-scan display is exactly like a B-scan display except that the view is oriented perpendicular to B-scan view in the plane of the plate. The D-scan allows quick discrimination of indications along a weld by presenting their position in depth from the scanning surface. An example of the relationship between all four common ultrasonic displays is shown in this figure. Types of displays of ultrasonic examination or UT number 5 is S-scan, or commonly called phased array ultrasonic testing or PUT, uses multiple angles to create a detailed cross-sectional image. Helps measure flaw size and location more accurately. The phased array S-scan display or sector display, see this figure, shows two-dimensional imaging of ultrasonic reflectors by plotting information from a multitude of angles simultaneously. The image is a cross-sectional view of the area where the ultrasound passes through. Location and size information can be measured for any reflectors that are in the sectorial scan. Phased array ultrasonics accomplishes this by using a transducer that contains multiple elements. 8 to 128 commonly, that are excited at intervals to create constructive interference in the wavefront of ultrasonic energy. This constructive interference is controlled by the amount of time delay in element excitation and can steer the sound through a range of angles. This array of beam angles is then plotted to create the sector scan. The ultrasonic energy provides responses in a pulse-echo fashion as with conventional straight beam and angle beam techniques. Types number 6 of ultrasonic testing is time of flight diffraction or TOFD. This technique is combined two techniques, those are B-scan and D-scan. TOFD is a special ultrasonic technique that uses diffracted sound waves, not reflected ones, to detect and size defects in welds. It uses two probes, one sends sound, the other receives it, placed on opposite sides of the weld. When sound hits a flaw, it causes vibrations that send diffracted signals to the receiver. The data is shown as B-scan that showing parallel view and D-scan that showing perpendicular view, built by stacking A-scan images. These scans use grayscale images to show signal strength and help measure the depth and size of defects. TOFD is especially useful for accurate sizing of flaws through the thickness of the weld. Requirements for ultrasonic inspection. According to ASME Section 5, Article 4, ultrasonic inspections must follow a written procedure. This procedure must include types of welds and materials, technique used, straight or angle beam, type of couplant, gel/liquid used to transmit sound, instrument type and calibration details, scanning directions, parallel/perpendicular, manual or automated scanning, evaluation and reporting standards, cleaning after inspection. Ultrasonic examination or UT system calibration, general calibration. Calibration ensures the ultrasonic system can accurately detect flaws of expected size and type. The system includes examiner, instrument, cables, transducer or search unit, couplant, and reference block. The transducer must be suitable, size, frequency, angle, to detect the smallest acceptable flaw. The reference block should match the test part in size, material, heat treatment, and surface condition. In the UT system calibration, calibration checks must be done at the following times, before and after each inspection, whenever equipment or personnel changes, every 4 hours during inspection, or more often if needed. Temperature of the reference block must be within 25 degrees Fahrenheit or 14 degrees Celsius of the test part. If not, adjust and recalibrate. For high-temperature inspections, special transducers and couplants are needed. If calibration fails, re-inspect all areas tested since the last successful calibration. Echo evaluation with DAC or distance amplitude correction. DAC curve helps evaluate unknown flaws by comparing their echo height to known reference signals. Echo strength decreases with distance due to material attenuation and beam spread. DAC is created by recording echo signals from known reflectors at different depths. The curve shows how signal strength drops with distance. Flaws are evaluated by comparing their signal to the DAC curve, for example 50% DAC, 80% DAC. Using the same material for reference and test parts ensures accurate compensation for material effects. To conducting ultrasonic testing, surface preparation before UT inspection. the surface must be clean and smooth, remove weld spatter, dirt, and irregularities to ensure accurate results. Examination shell coverage includes, inspect the weld, heat affected zone or HAZ, and nearby base metal, move the transducer across the surface with 10% overlap between passes. Scanning speed should not exceed 6 inches or 152 mm per second, unless verified. Oscillating the transducer helps detect fine cracks in different directions. Here a detail of ultrasonic examination or UT techniques. The first technique is straight beam examination. It used near the weld to find flaws, like laminations, that might block angle beam inspection. All such flaws must be recorded. The first technique is angle beam examination. There are two types of angle beam examination technique. Number 1 is parallel to weld, beam is perpendicular to weld. Number 2 is transverse to weld, beam is parallel to weld. Scanning is done from both sides and at higher gain for detection, but evaluation is at normal sensitivity. For transverse flaws, rotate the transducer 90 degrees or use other techniques. Supplemental shear wave examination. TOFD may miss flaws near the surface due to strong signals. ASME requires angle beam inspection of top and bottom weld surfaces, ideally perpendicular to fusion lines, can be done manually or automatically, often combined with TOFD. Automated ultrasonic testing or AUT. There are 4 main AUT techniques for weld inspection. The automated ultrasonic testing. Number 1 is pulse echo raster scanning. It uses straight and angle beams from both sides. It detects corrosion and weld flaws. Automated ultrasonic testing. Number 2 is pulse echo zoned inspection. It is a line scan with multiple transducers. It covers full weld volume using set angles and timing. Automated ultrasonic testing. Number 3 is time of flight diffraction or commonly called TOFD. It is a line scan using pitch catch method. It may need multiple transducer sets for full coverage. And automated ultrasonic testing. Number 4 is phased array or commonly called PUT. It uses multiple elements to steer and focus the beam. It allows inspection of specific zones with various angles. Discontinuity evaluation and sizing. In general, UT procedures must include how to evaluate and size flaws. Flaws that exceed a certain percentage of the DAC curve must be checked against acceptance criteria. One common sizing method is the 6 dB drop technique. Maximize echo signal and mark the spot. Reduce signal to 40% or 6 dB drop by moving the probe left and right. Mark both points to estimate flaw length. There are 5 discontinuity evaluation and sizing methods commonly used. Methods. Number 1 of discontinuity evaluation and sizing is ID creeping wave method. It uses different wave types, longitudinal and shear, to estimate flaw location in top, middle, or bottom third of the wall. ID creeping wave method involves high-angle longitudinal wave up to 70 degrees. 30 degrees shear wave converting to longitudinal. And head wave traveling along the surface. Methods. Number 2 of discontinuity evaluation and sizing is tip diffraction method. It is effective for flaws open to inner, ID, or outer, OD, surfaces. It uses wave paths to measure flaw tips and depth. Methods. Number 3 of discontinuity evaluation and sizing is high-angle longitudinal method. This method good for deep flaws, especially in coarse-grained materials. It uses focused probes with high-angle longitudinal waves 60 degrees to 70 degrees. It helps in detection and confirmation of flaws. Methods. Number 4 of discontinuity evaluation and sizing is bimodal method. This method uses dual-element probe to detect flaws in mid-wall region about 30 to 60%. This method combines multiple wave conversions to detect flaw base and top. It may oversize shallow flaws and undersize deep flaws. This method requires advanced training to use effectively. Methods. Number 5 of discontinuity evaluation and sizing is phased array method. This method uses multiple transducer elements to steer and focus the beam. This method can scan manually, semi-automatically, or fully automated. This method provides multiple views, A scan, B scan, C scan, sectorial scan. This method efficient for data collection and flaw analysis. Thank you.